All right, so we're finishing 3.2, starting 3.3. Get your calculators out if you don't have them already. Did anybody else have any homework or assignments they wanted to turn in? Anybody? Nothing was due today. If I haven't, I'm going to put zeros in the grade book for anything that I have missing. That doesn't mean you can't turn it in. That just means I don't have it, so turn it in ASAP. I'm also undo it. Yeah. I'm also grading all your guys' tests this weekend, so all that will be in. If you know that you're missing a test, I need that made up on Monday, sooner than later. That is not graphing, so you can either just watch us. Use the app. Yep, or use the app. Cool. So I know we're all in a couple different places. My goal for break is to get caught up on your grade, so everything has been graded, everything's up to date. Your job over break is, if you're missing anything, to get caught up on that. We are going to quiz on November 30th. I believe that's a Wednesday, on 3-1, 3-2, and 3-3. And then on Wednesday, December 7th, we're going to have a test on everything we've done in Chapter 3. I believe that will be all the way through 3.5. The only thing that will not be on the test that will be on the final is 3.6. We'll have a couple more days to work on that. But that being said, we got some vocab or some word problems that we need to get into today. So we've got 5 word problems, and then we're going to do some log rolls. Does log roll mean anything to you? Great, I'm going to teach you all about it. So first, these first couple word problems already have equations written, which is so nice. This first one is about the spread of flu. It says the number of students infected with flu at Springfield High School after T days is modeled by this function. So yes, very nice of them. They gave us our function that we need. What is the initial amount of infected students? What point would that be? What would tell me my initial amount? What would I need to do to find the initial amount? Plug, I don't even plug 1 in, even lower. 0. On day 0, what did we start with? So we're going to say t equals 0. We're going to plug 0 in for my t. So I can think of this as p of 0 equals 800 over 1 plus 49 e to the negative 0.2 times 0. Now, negative 0.2 times 0 is just 0, and anything raised to the 0 power is just 1. So now that e raised to the exponent canceled, so I get 800 over 1 plus 49, which is going to be 50.
Thank you.
You're welcome. Thank you for coming. Your friends were talking some crap.
Oh, they sound these kids.
Well, I'll just tell you. But you did not. You were definitely here. So, and you've only missed like 20 seconds of our notes. Yeah. 800 divided by 50 is going to be 16. So the initial amount of students that was infected was 16 students. Not too crazy. The next problem says, when will the infected number of students, or the number of infected students, be 200? What do I do with that 200? Good. Barrett says 200 equals. So that means I'm going to set my equation equal to 200. This is why I told you to get your graphing calculator out, is because I'm not going to algebraically solve this. I'm going to say 200 equals 800 over 1 plus 49 e to the negative 0.2t. Eventually, I'll teach you how to solve something like this by hand, but we don't have to, and let's work smarter, not harder. So I'm going to plug one of these in for y1. I'm going to plug the other one in for y2. We're going to do a lot of graphing today, so be comfortable with this. My only suggestion, I'll just say it now and I won't lecture on it again, is I encourage you to go back and figure out how we found these windows. It's really easy to like watch the board and be like, oh yeah, like I know how to enter in like 200 for my y1, and I can put that big ugly fraction in to y2. And then once you have the graph, you're probably good at finding the point of intersection. But sometimes we struggle with the like window. And I'll tell you my thought process for the window, but I also need you to practice how to find the window on your own. I promise there'll be a question on the quiz, something like this, where you're going to have to find a window. And so I'd be prepared to know how to do that on your own. To me, I know I need to be at least bigger than 200. I'm probably going to be closer to 800, that numerator of my window. So my y max is going to be 800. And my x's, I'm not quite sure what that's going to be. I might try something as small as like 20 and see what happens. If I cannot see the point of intersection, I'll just make that 20 a bigger number. Oh, but I see it. Graph, I see my point of intersection. So I'm gonna go second, trace, intersect, left bound, right bound, enter. My intersection is at 13.96, which is about t equals, we'll call that 14 days. My x value is the t, and we know t is time. And in this equation, time is in reference to days. So the question said, when will the infected number be 200? And so we set the equation equal to 200. Anybody questions on that or the graph?
How do you do the E in the graph?
Great question. If I'm going to my y equals, I'm entering that E in, press second ln, and it gives you an E with like a little exponent already ready for you. Yeah. I did 0, 20 for my x's, and then my y, I did 0 and then 800. Yeah. I just guessed. So I thought it would not be too big. But like, let's say I guessed wrong. Let's say I guessed 10 and I looked at my graph and I see that they don't cross each other yet. That just means I need more on my x. So then I'd go into my window and press something bigger. I could have also done something so big like 100, which like maybe doesn't seem right, but then I can definitely see where my graph intersects. So sometimes I go a little bit bigger, better safe than sorry. But every so often the graph is so zoomed out that you can't really tell what's going on. So I want to be a little intentional. X's are usually not much bigger than like 100 or 200. So I try not to get too crazy with my X's. All right, the next one says, the school will close when 300 of the 800 student body are infected. When will the school close? How do I figure that one out? Is that one like A or like B? Am I going to plug 300 in for my X, or am I going to set 300 equal to my equation?
Probably 300.
Definitely 300 equal to my equation. Yeah, very good, Zach. 300 is going to go equal to my equation because I want to know WED, which is in terms of T for time. So I'm going to say 300 equals 800 over 1 plus 49 e to the negative 0.2 t. And just like I did before, I'm going to set 1 as my y1 and 1 as my y2. The only thing I'm going to change here is make my y1 300. I'm actually going to leave my max and min and all that stuff the same. I was just playing around with my window, but I think even if I left my x max at 20, I still think it'll be okay. Yeah, there it is. I can still see where my graph is, so I'm going to do my second trace intersection. Left bound. Oh. Every 5 minutes, it just decides to quit out on me. Second trace intersect. Left bound, right bound. Oh, where are you? So this is 16.9, which I'm going to round that to 17. So T equals 17 days. So it took a long time to go from 16 students to 200 students, but it took a lot shorter time to go from 200 to 300 students. All right, how are we doing? Good? All right, moving on. Next one's super similar. So that's why my calculator's still up. This one says the population of deer after T years in Cedar State Park is modeled by this function. It looks super similar to the last one. Letter A says, what's the initial population of deer? What do I do to find the initial population? 0. 0 where? For my T, very good. T is going to equal 0. So we're going to say P of 0 is equal to 1001 over 1 plus 90 e to the negative 0.2 times 0. Now, just like last time, negative 0.2 times 0 is going to be 0. 0, e raised to the power of 0 is just 1. So I'm left with just 1001 over 91. And I actually think I can do that on my calculator, 1001 divided by 91, and that equals 11. So my initial population of deer was 11 deer. Rewrite deer to make it look good. There we go. All right, initial population is when t is 0, when time is 0. All right, letter B says, when will the number of deer be 600? What do I do with 600? Good, set it equal. So we're going to say B is 600 is equal to my equation 1001 over 1 plus 90 e to the negative 0.2t. And then what do I do now? What did we do last time we had an equation like that? Calculator. Yeah, Ryan. Yeah. That's what you're going to say? Good. We're going to graph it, right? Put one of them in for y1, put one of them in for y2. We got to play with my window a little bit. How high do you think my y should be?
700.
I can go even higher than 700.
And
Let's go. You see how the numerator says 1001? Remember how we did these logistic functions and my asymptotes were at 0 and then whatever the numerator is? So that means it's never going to go higher than 1001. So I'm actually going to make my y max 1000 or maybe 1010 or 1001, something that's a little bit bigger than 1000 so I can see my whole graph. I bet we'd see the intersection at 700, Barrett, but if we wanted to see more of it, I would go all the way to 1000. And then I actually don't know what my x is going to be. I'm going to keep it at 20 and see if that's good enough. Graph. Ooh, not quite good enough. I might go to 100 just so I can ensure that I'm going to see it this time. Oh, perfect. Got a really nice logistic graph going on here. Now I'm just ready for the intersection. Second, trace, intersect, left bound, right bound. My intersection is at 24.5. When I'm talking about years, I'm going to round that up. So if it was at, in the year, 24 years after it started, it would not quite be at 600 population, but by the year, at the beginning of the 25th year, it would be at that. So I'm going to say T is equal to 25. Yep. All right. And then letter C says, what is the maximum number of deer possible in the park? 1001. Very good. Just like we talked about literally 2 seconds ago, Barrett knows that 1001 is like the maximum that we can have. It's my horizontal asymptote. The other word I used for it was limit to growth. So we can't grow any more than 1001. That's my limit. That's the most amount it can be. Are we doing okay with these? Perfect. Okay, the next 3 word problems are going to be all exponential functions. Remember the exponential that I told you about? I taught this to you last class. It was P of t is equal to P of 0, 1 plus r raised to the t. So this was a function, an expression, a formula, whatever you want to call it, that we're using now to represent these exponential functions. So P of 0 is my initial value. Let me zoom out so I can read the problem. Let's see if we can see our initial value. I'm going to make my calculator a little smaller. I don't need it that big. Okay, population of Smallville in the year 1890 was 6,250. Assume the population increased at a rate of 2.75% per year. All right, it doesn't ask us for this, but let's find an equation to set this up in. We're going to still use P of t because that's function notation. What is my initial value? What's my initial amount? Good, 6250. I'm going to do 1 plus, what's my rate? Good, I like that you put it as a decimal point, 0.0275, and then it's all being raised to the t. The only thing I'm going to do before I start plugging things into it, I'm just going to add what's in that parentheses. I'm going to say P of T is equal to 6,250 times 1.0275 raised to the T. All right, now letter A says estimate the population in 1915 and 1940. If I started at 1890, how many years has it been since 1890 to get to 1915? 25. So we're going to plug in 25 for my T. And then we're going to do something similar for 1940, but let's just do one at a time. So 6,250 times 1.0275 raised to the 25th. I think you can put that all in your calculator at once. 6,250 parentheses 1.0275 end your parentheses. Remember that you can raise anything to any exponent. If I do the caret button, the button that's between clear and division, that raises it up to be an exponent, and I can put any number up there. So that's going to be 25. 6,250 times 1.0275 raised to the 25th is this big number. Unlike years, for people, I'm going to round down because 0.75 is not a whole person by the time. So we're going to round it down to 12,314 people. Bless you. That's 25 years later. Did I see a hand? We're going to do the exact same thing for the next one. However, this one says from 1890 to 1940. How many years is that? 50. Good. So we're going to plug T in, 50 in for T. I'll be quiet while you do that. And I am going to round this down. You guys doing okay plugging in those big numbers as the exponents? Okay, awesome. All right, letter B says predict when the population will reach 50,000. What do I do with that 50,000? Do I plug it in for T or for Y? Good. I plug it in for Y, so it's 50,000 equals. And it's still 6,250, 1.0257275 raised to the T. Go ahead and put those in for your Y1, Y2s, and then we're going to deal with our window. Play around with it. It's going to be really big. See if you can come up with the window on your own, and then we will compare it together. Take a second, plug this into your equation. Give me 1 second, I'll join you. Yeah, I wanted these on this line, and then I want this so that it's so I so, and some of them have it, but anyone that does have it, I want you to use moving on. Do you have any questions? As long as I can tell what you're talking about. It doesn't have to be exact, but I need to like know a little bit of what you're saying. All right, let's look at this window together. I am going to do, let's see, Y equals 50,000. Raise to the T. I am gonna tell you my my Y max is gonna be really, really big. My Y max has to be bigger than 50,000. I'll probably make it 80,000 and see what happens. And I'm actually gonna leave my X max at 100 and see if that's good enough. Oh, that is good enough. Oh, there's a lot going on over here. All right, so you see that point of intersection? I'll make my graph a little bit bigger since we're looking at that. Let's do our second trace intersect to find out my left bound, my right bound. It looks like it intersects at about 77. 77 years. All right, cool. Let's flip our paper over. We had 2 more word problems, and then we got some log rolls.
Yeah, 2 straight lines.
You got 2 straight lines?
Yeah.
Your X max is probably not big enough. Let's go to your window. What's your X max?
100.
Make it, oh. Should be 100. What was your Y max?
250 times 1.0275.
Oh, not to the 50th. You want it to the T. Because the 50th is actually, like, it's going to give us a number there.
Okay.
So put it to the T, so it's actually a variable. So you delete, or go over one more. Delete, and then X. Now it should start doing something.
Very slowly.
Very slowly. All right, this next one says, the 2000 population of Jacksonville, Florida was 736,000 and was increasing at a rate of 1.49 each year. All right, time out. Let's write our equation. We're going to say P of T equals, what's my initial value?
2,000.
That's a year.
Oh, I mean, 736,000.
Good, 736,000. Is it going to be plus or minus? Plus, why? Good, increasing, it's raising. And what's the rate?
0.01.
Yeah, 0.0149 raised to the T. All right, the only thing I'm going to do on this left or this right side is simplify inside the parentheses. 736,000, 1.0149 T. And then my question says, when will the population be 1 million? Does 1 million go for my T or for my Y?
Y.
Y, very good. 1 million is a 1 with 6 zeros after it. Whenever I have an equation that looks like this, what should I do? Graph it. Y1 is 1 million. Y2 is going to be 736,000 times 1.0149 raised to the X. I'm going to tell you my max needs to be bigger than 1 million. I might make it 1.5 million or whatever to see if I can get it big enough. I do think my X max is probably good at 100. I'm going to leave it there. I'm going to make my Y max 1,500,000. That's 1.5 million. 1,500,000. Oh, perfect. I see it. I know it's probably small on the board for you guys, but there it is. Just like everything, second trace intersection, left bound, right bound, enter. It's about 20.7. So we'll say T equals 21 years. Which is actually interesting. Yeah, Billy. Yep. If it said that in 2000, it was going at this rate, then 2021 was last year. So I wonder if the population of Jacksonville is 1 million. It'd be an interesting stat to look up. All right, I've got one more and then I've got some logs to do. This one says radioactive decay. The half-life of a certain radioactive substance is 65 days. There are 3.5 grams present initially. Okay, half-life is a little weird. Half-life means that we're decreasing by 50%. So half-life means a decrease by 50%. The base is going to be 1/2. PFT, I don't know why I did it like that. Yep. Oh yeah, I mean you can go down and go here. PFT equals 3.5, and then the number that's getting raised to the exponent is going to be 1/2. Think about if we're decreasing by 50%, that's like 1 minus 0.5, and 1 minus 1/2 is just 1/2. So that's the 1/2 inside that parentheses. Now, the only thing that's weird about half-life is it takes a few days to actually do that. So this time it takes 65 days. Anytime it takes like a couple days or a couple weeks or a few years or however many, we're going to not just do t as my exponent, we're going to do t divided by however many days, years, months, whatever it takes for the half to actually happen. So I'm going to say P of t equals 3.5 times 1/2 raised to the t divided by 65. All right, that's all at once for letter A. Express the amount of substance remaining as a function in t time. Perfect. The only difference for letter B is it says, when will there be less than 1 gram remaining? What do we do with the 1 gram?
Oh, probably
not T. It's my P of T, it's my Y. I want to know when will there be less than that. So that's a bigger number. I want to know when my 3.5 has gotten down to less than 1. Now, if you don't like writing 1/2, you can write 0.5 in that parentheses. Both mean the same thing to me. But we're going to go put this in our calculator again. The only difference is, remember the last one, my Y1 was 1,000,000. Now my Y1 is going to be 1. So we're going to have a much smaller scale. We're going to have to really change our maxes and mins. 3.5 times 0.5 raised to, now since I'm doing t divided by 65 as my exponent, I do like to put parentheses around it, x divided by 65. My window, I do not need to be at 1.5 million. I probably only need to be at 5. If I started with 3.5 grams, I'm not going to get any bigger. I'm getting less. So I could even start lower than 5, but 5 is probably pretty good. And then my X max, I'm going to keep it out at 100. If I need to make it bigger or smaller, I will. But I'm going to try here and see where we're at. Ooh, I'm so close, but not quite. I'm going to have to go a little bit bigger than 100. Let's make that 200. Okay, perfect. Now I can see that intersection. Let's do our second trace intersect. My X max was, I was originally 100, and then I just changed it to 200. You're welcome. Left bound, right bound. It looks like they intersect at 117.4. We'll round that up to 118 days. T equals 118 days. All right, we are going to get into 3.3, but I do want to take a quick team timeout. This is 3.2. You have homework due on this on Monday. We are going to start 3.3 right now, but we're going to finish that on Monday. The quiz, or I guess I don't see you guys till Tuesday, so all of this is Tuesday. The quiz that you're going to take on Wednesday will only go up through 3.3. So we should get past that next class, but it will only go up through 3.3 at max.
So you use the greater than star instead of the star? If you have to put it greater.
You don't technically need that.
Are you just saying that so if we know?
Just so we know. Also, then when we look at the graph, we want everything below the line of 1. So I knew to go to the line of 1, and then everything after 118 days works. All right. So in the last few minutes of class, we're going to do what I call log rolls. You're welcome. Awesome. Thank you so much. No problem. Go ahead and work on the rest of chapter 4 stuff, and we'll talk on Monday, okay? I might send you an email kind of with my thoughts too, so just think about that, all right? Okay. Thanks. What? Bye. Have a good break.
Can I, which one to you?
Yeah.
Can I I submit homework online?
Yeah. Yeah, I'll see it. It's easier for me if you submit it to Schoology than it is when you email it to me, because things in my email just get buried down. So sometimes I lose it. So yes, I'd rather you submit it to Schoology. All right, so what we're about to talk about now is something called a log roll. Have you guys heard of that phrasing before? Some of us are saying yes, some of you are saying no, some of you are just like not quite sure. That's okay. I think every teacher teaches logs a little different. This is how I teach logs. I like to think of the general log looking something like this. Log of B, log base B of A equals X. This is what a logarithm looks like. The little b is the base, A is what we're doing the log of, and then X is what all of it equals. When we do a log roll, I'm going to start on the first number I see, which is the B, the base. We're going to start at base. We're going to go underneath the equation and loop around to X. And then we're going to thread the needle back through and go to A. Do you see how that yellow line I made kind of looks like a lowercase e? That means that I'm going from log to exponential. So I started at B, I went through X, and then I finished through A. My exponential form of this is going to be B raised to the X equals A. So the log roll, as I touch each letter, that's the order that I write them in. So I started with B, then I went to X, then I finished at A. So B raised to the X equals A. We'll go the similar way, but going backwards later. But right now we're going to start here. All of these, I'm going to treat them as equals X equals X equals X. So if it doesn't have equals X written next to it, I would say equals X, because that's going to help us do our log roll. I'm going to start at my base. So the first one, my base is 5. I'm going to wrap around from 5 to X and then finish through 5. So the exponential form of this is going to be 5 raised to the X equals 5. When I do this, when I do my log roll, I get rid of the log. I don't need to write my log anymore. It's just a new exponential form. And now I see an equation that says 5 raised to the X equals 5. What raised to the 5 raised to what power gives you 5? 1. Awesome. That was easy. It's a lot easier to see what my answer is when we roll it around like that. All right, let's do it for the next one. I start with 4, I loop around to X, and I finish through 16. So that exponentially would be 4 to what power equals, good. And what would X be? 2. Oh, great job. Ooh, the next one looks a little funny. It says ln. ln means natural log, and that's the same thing as log base e. So this ln means log base e of e to the 10th. That means my base on the other one, see how my base was physically written? My base here was not written, but since it's ln, it's implied that it's e. I can think of there as being like a little bitty e right here. So I'm still going to log roll the same way I've done. I'm going to start with e, loop through X, and then finish with what we're doing the log of. E to the X equals e to the 10th. E raised to the X equals e to the 10th. And so e to the X equals e to the 10th. What does X have to equal? 10. All right, we didn't get as far here as I wanted to, but that's okay. 3.2 is due on Tuesday.